A question was asked about what is going to be on the assignment sheet. So let me show you what I'm working with, and I'm probably like I know for a fact I need to fix some of this stuff. So up here on the top of this particular sheet, I have MOSFET current voltage characteristics. So I have a picture of a MOSFET, an NMOS device defining VGS, VDS, and ID, how cutoff region is defined, how the triode region is defined, and then I have an equation for transconductance here, which you guys actually won't need, so I'll probably wind up pulling that off. Over here, I have what's going on, the conditions for saturation, and then again, transconductance stuff, which I'll pull off. Similar thing for cutoff mode, or excuse me, for PMOS devices. Brain was not working. And then if we scroll down here, I have the circuit diagram for the 4-resistor bias network. Up here are our relationships for yeah, so this is the polynomial, but I'll probably, so this is an older one. I'll go back and I'll fix this to specifically give you just the VGS equation and all of that kind of stuff, and the VDS equation, only with channel length modulation neglected, because like I said, I can't make you work anything where channel length modulation is included. And I can't actually make you come up with a numerical solution for anything that's in the triode region, because you'd be solving a system of equations where some of those coefficients are going to be for squared terms and all of that kind of stuff. So your calculators literally can't solve that system. But so layout similar to this. So NMOS device, associated equation, PMOS device, associated equation, NMOS device for self-biasing, associated equation, NMOS device for self-biasing, associated equation. For the BJTs, it'll be something similar to that, where I'll just have a diagram and then the equations for all of the different currents and all that kind of stuff as a function of VBE and how they relate to each other. And then I'll probably do a little thing with the biasing circuitry and effectively the KVL and KCL and all. Actually, so I'm thinking about not doing the KVL and KCL for the BJTs, because you need to do something. It isn't literally just use this thing and then regurgitate my work at you and congratulations on the 100 on your exam. It should require some amount of thought on your part, so I'll probably leave the BJT biasing circuits off and expect you to be able to figure out how to do all of that kind of stuff like I did on your homework. So, yes.
A lot of the homework I found, like adding math calculus system equations, BJTs with exponential and everything. On the exam, what kind of circuits could we expect to be able to hand solve?
So there shouldn't be any early effects type questions, because those are the ones that should explicitly require you to solve a system of equations. But without the early effect there, you should be able to solve for VBE just using the one equation, one unknown solver. Use that to solve for your collector current, and then knowing your collector current, then you then know your base current and your emitter current, which means you should be able to solve for VCE from that. So only one equation, one unknown system type thing that can't make you solve for anything more difficult than that, because it will literally require the use of a computer. Yep. Yes.
With the modes of operation.
Yeah, I'll put that on there. I'll probably put everything in terms of VBE and VCE, and that's it. Yeah. So meaning that if VBE is, if VCE is greater than VBE, it's greater than 0, it's in forward active region. If VBE is greater than VCE is greater than 0, that would be saturation kind of thing. And then cutoff is effectively VBE is less than 0, doesn't work. And we won't worry about reverse active because, like I said, it's never intentionally that. So, okay. So told you what's going to go on the equation sheet. Now I just have to finish doing it while doing all of my other stuff. It is what it is. All right. So today we're going to talk more formally. It's doing that about using transistors as amplifiers, and we're going to start by looking very formally at how a BJT amplifier works. This is going to more or less rederive our small signal model for a BJT, but with a little bit more context. And then we're going to apply all of that to MOSFETs, and then we'll be off to the races. All right. So introduction to amplifier circuits. So we're going to start by looking at a simple BJT circuit. So here is our supply voltage, VCC, some resistor, RC, our transistor will be here, and here's effectively the output terminal of our device. And so let me explain what my subscripts and all of this kind of stuff are going to mean. So right here, I've written capital VBE. So this represents a DC signal. So this is the part that's establishing the DC operating point of this circuit. And then in series with that, I have a lowercase VBE. So that lowercase stuff means it is going to be a small signal thing. So let me write that over here. Uppercase is effectively large signal. Lowercase will be small signal. And then we're also going to have things that are mixed. And so what I mean by that is I'm going to draw this thing right here, lowercase v, capital VE. And so when I have a mixture of upper and lowercase, it is combination of large and small signals. Excuse me. So due to this total voltage drop applied across the base emitter terminals of this junction, we should see some mixed current, IE, flowing through the emitter, some mixed current, IC, flowing into the collector, some mixed current, IB, flowing into the base, and we should see some mixed collector emitter voltage as well. Okay. So in this circuit, our small signal voltage, VBE, is much less than our thermal voltage. So effectively, we're talking about something in the ballpark of 5 to 10 millivolts, possibly less, right? So what we're going to find is that single transistor amplifiers do a very, very good job of small signal amplification. They do a significantly less good job on large signal amplification, where a large signal amplification would be something that's any signal that's large enough to actually push it out of, in the case of a BJT, the forward active region of operation; in the case of a MOSFET, the saturation region of operation. So we're restricting ourselves to incredibly small signals that we are trying to actually amplify with these things in order to maintain that our device stays in the mode of operation that is most conducive to it acting as an amplifier. So if we neglect the perturbation caused by the small signal voltage VBE, we would have the relationships IC is equal to IS times the exponential of VBE over VT. IB is equal to 1 over beta times IC. IE would be beta plus 1 over beta times IC. And our DC collector emitter voltage would be VCC minus IC RC. And all of these equations effectively establish the DC operating point of the device, which is what we've been working on figuring out up to this point in the class. If we include the perturbation, we get the mixed base emitter voltage of capital VBE plus lowercase VBE. And this will in turn give us a mixed collector current, IC, is equal to IS times EXP of capital VBE plus lowercase VBE divided by our thermal voltage. And we can split this up as IS EXP of capital VBE over VT times the exponential of lowercase VBE over VT. And this looks like our DC collector current, IC, EXP of lowercase VBE divided by VT. So when VBE is much less than VT, the exponential of lowercase VBE over VT will be approximately equal to 1 plus lowercase VBE over VT. So I'm trying to remember gonna annoy me that I can't remember what this is technically called. Oh my God, it's annoying me that I can't remember this. So it's a math thing where you're representing a function by a summation where you have like your first order term, your second order term, all that kind of stuff. What's that called? Taylor series expansion. Okay, exactly right. So this is just the first order Taylor series expansion where we're leaving off all of the second order and higher terms. Thank you for that. Okay. So I'm not pulling this out of thin air. This is something that you guys have hopefully seen before. And so recognizing that when VBE is much less than VT, the exponential behaves that way. What we come out seeing is that our mixed collector current is approximately equal to IC times 1 plus VBE over VT, or IC plus IC divided by VT times lowercase VBE. So we have some DC component here, or let me write that DC better. Large signal. And then we have some small signal component, typically AC, here. Where our small signal, lowercase I, lowercase c, and I understand that lowercase c and capital C are very hard to tell the difference between in my handwriting, so I'm telling you explicitly, that's a lowercase c. We get IC over VT times VBE, and we call that ratio of IC over VT GM, the transconductance. Where this is nothing more than the partial derivative of our collector current with respect to our base emitter voltage when our mixed signal IC is equal to our DC. So we're going to see this definition a couple of times today. Transconductance being the partial derivative of a current with respect to a voltage. And I believe I've said this before, but what the transconductance represents is effectively how well a input voltage, in this case, small signal VBE, gets translated into an output current, in this case, small signal IC, in a transistor circuit. So I'm going to draw a graph here. This is I, lowercase I, capital C, by the way. And this is lowercase v, capital BE. And so if I were to plot my DC portion in red, it would look something like this, right? So we know that we have an exponentially increasing current. Something like that. And let's define this point right here to be our DC operating point. So if we allow a perturbation to be superimposed on top of that voltage VBE, something like this, what we'll wind up seeing is a perturbation on the output portion, in this case, our current. That's going to look something like this. So where this pink curve here represents lowercase I, lowercase c. So what we are seeing here is a small variation in the input voltage yields a large variation in the output current. The slope of the tangent line at the DC operating point is literally what the transconductance represents. So hopefully this picture here will explain why we want, in the case of a BJT, our device to be operating in the forward active region of operation. Our transconductance is higher the further away we get from down here. So we want our device to be biased such that our transconductance is as large as possible, because that gives us the largest possible variation in the output current due to the smallest variation in the input voltage. Okay. This is exactly how amplification occurs. Yes.
What are the squigglies between the two dotted lines first?
Yes, squiggly. This is the signal. So these are just the bounds showing us the magnitude of the variation. Okay. This is the perturbation in the voltage VBE, giving us this perturbation in the current IC. Okay. Yes.
What is the
Slope.
on that slope?
Literally the word slope. The slope of this purple line is the transconductance. So that is the slope of the tangent line at the DC operating point, right? So if our DC operating point were somewhere down here, our slope would be lower, our transconductance would be lower. Ideally, we want our slope somewhere in this portion of the curve where the slope is very, very high, because that means we have a very high transconductance. Righter. Yep. We do. We put some input signal there. So we establish some DC operating point, and then we have something that we want to amplify, some small signal that we want to amplify. So that could be the output of some sort of sensor that's only capable of giving us very, very small voltages due to how it responds to some external stimulus. That external stimulus could be literally anything, right? It could be a piezoelectric transducer, which converts mechanical deformation into a small electrical signal. Could be a nickel strain gauge or something like that. Just anything that gives us an output voltage due to some sort of external response or external stimulus. That being said, supply voltages and all of that kind of stuff might have noise on them, which will wind up causing perturbations as well. But for this intents and purposes of what we're talking about right here, using the device as an amplifier, we are supplying the perturbation. That is something that we have control of. So we are purposefully pushing the signal slightly away from its DC operating point in order to achieve some form of amplification. All right, so we have established that the perturbation in the input voltage VBE causes a small signal current IC to flow. Because IC and IB are related to each other, we should see some perturbation in the base current as well, right? So our mixed signal base current, lowercase I, capital B, is going to be simply our mixed collector current, lowercase I, capital C, divided by beta. And this becomes IC over beta plus 1 over beta times IC over VT times lowercase VBE, right? So once again, we have a DC term, this guy over here on the left, and then our small signal or AC term over here on the right. So from this, we can observe that our small signal base current is just 1 over beta times IC over VT times lowercase VBE, which is nothing more than our transconductance divided by beta lowercase VBE. So there is a linear relationship between our perturbation voltage VBE and our perturbation base current. And anytime I have a linear relationship between current and voltage, I say, hey, that looks like a resistor. So we can define the resistor R pi to be the ratio of VBE to IB, both small signals, which is just beta over GM, or VT over IB, or beta VT over IC. All of those are literally the exact same expression, just depends on what information we have. If we have our transconductance, we can use this guy. If we have our base current, we can use this guy. If we have our collector current, we can use this guy. They all represent literally the exact same thing. So with early effects present, so when early effects are present, there is also a change in IC, where this is lowercase I, capital C. Due to the change in VCE. And this change also manifests itself, excuse me, as a resistance, which we've called R naught in this class. And so this is simply the partial derivative of our collector current with respect to our collector emitter voltage when our base emitter voltage is held to some constant value. And then we take the reciprocal of that because we don't want current over voltage. We want voltage over current to look like a resistance. And this winds up just becoming our early voltage VA divided by our DC collector current. So putting all of this together, we wind up having a small signal model that looks like this. So here's our base terminal. Our resistor R pi that's representing the perturbation in the base current as a function of the perturbation in the base emitter voltage. So here's our small signal voltage VBE. And for reasons that I literally do not know, we very often call this voltage V pi. This current source here represents small signal collector current IC, lowercase I, lowercase. And in parallel with that, we have that resistance R naught due to the effects of the presence of the early effect. This is our emitter terminal. This is our collector terminal. And so here's lowercase I, lowercase b, lowercase I, lowercase c, lowercase I, lowercase e, our small signal currents in this system. So here's a formal derivation of where small signal model or a BJT amplifier comes from. So we are going to see something similar now when dealing with a MOSFET. I'm not going to go through an elaborate as explanation of what's going on in a MOSFET because it's going to work the exact same way. Some small change in our gate source voltage is going to cause a change in our drain current. That's going to manifest itself as resistors and this, that, and the other, right? Okay, so the first thing that we talked about, so let's go underneath here. So the first of the small signal parameters that we figured out for a BJT was the transconductance. So now let's figure out what the transconductance is going to look like in a MOSFET. So in a MOSFET, our transconductance is defined as the partial derivative of our drain current with respect to VGS when VDS is constant. So using this definition, we get mu n C ox W over L times VGS minus VTHN for an NMOS device, and then obviously for a PMOS device, this would be mu P, and this would be the absolute value of VTHP, right? So this is the expression that we can use when we know what mu n Cox, size of the transistor, and all that kind of stuff is, and we also know VGS. This can also be written as the square root of twice mu n Cox W over L times our drain current. Or it can also be written as twice ID over VGS minus VTHN. So three different representations, just depending on what information is available to us. And all three of these are valid in the saturation region of operation. Without channel length modulation. With channel modulation, this is going to look like mu n Cox W over L VGS minus VTHN times 1 plus lambda VDS, or the square root of twice mu n Cox W over L ID divided by 1 plus lambda VDS, or this guy up here again, since this one is dependent on both VGS and ID being known, it automatically takes into account the channel length modulation as well. So we've got our transconductance relationship for the saturation region. There's also a transconductance relationship for the triode region, but we don't really worry about that because we're never really supposed to be using an amplifier that's working in the triode region, because that's by definition, our transconductance will be lower in the triode region, which means we're not getting as much amplification as we could. All right. So this is our normal transconductance. So let me put here saturation with channel length modulation. Now, we also potentially have to worry about a transconductance due to the body effect. Yes. So this guy right here, if we calculated ID, the DC operating point of our drain current with channel length modulation effects already included, it's already buried inside of that effect. All right, so body effect transconductance arises because The potential difference between the source and the body of a MOSFET has a effect on the threshold voltage, VTH, which we've discussed previously, which in turn has an effect on VGS minus VTH. And so if it's going to have an effect on the overdrive voltage, and we know that our current is dependent on the overdrive voltage VGS minus VTH, we're also going to have some transconductance here. So our body effect transconductance is typically given by the symbol GMB, and it is the derivative of our drain current with respect to our body source voltage, which comes out as mu n Cox W over L VGS minus VTHN times the derivative of our threshold voltage with respect to the voltage VBS. Since the derivative of our threshold voltage with respect to voltage VBS is just the negative of the derivative of our threshold voltage with respect to this source body. So if I flip the subscript down here, I'm just getting a negative sign there. And then using our relationship for threshold voltage as a function of source body voltage, this winds up becoming negative 1/2 gamma times twice our contact potential plus VSB, all of this to the negative 1/2 power. And from this, we find that GMB is simply our regular transconductance times a factor of gamma over 2 square root of 2 pi F plus VSB. So effectively in our small signal model, we should expect to see up to 2 current sources in our device because we have 2 different variations in our drain current caused by different voltages. We are also going to have okay, so actually before we talk about that, all right, so we covered our transconductances similar to how we covered the transconductance for BJT. The next thing that we talked about in the BJT was the linear relationship between our base current and our voltage VBE, right? Which was how the resistance R pi came about. Does our gate current change with VGS in a MOSFET? Does our gate current exist? Not really, no. So this is a little something that might seem a bit odd, but we know in a DC circuit, DC MOSFET circuit, our gate voltage is 0. And we've been saying it's 0 because effectively the gate forms a capacitor with the substrate and all of that kind of stuff. So for DC, no current whatsoever. For small signal, we're also going to say that it forms a capacitor, but we know that capacitors have impedance, right? So we need to be careful about what frequencies we're talking about, okay? So the internal capacitor in a MOSFET is usually incredibly small. And actually, there's like 4. But we're talking on the order of picofarads to femtofarads. So as long as we're not trying to amplify a signal that's in the megahertz to gigahertz range, those capacitors are effectively still going to look like open circuits to us. And we'll talk about that in much more detail when we get into frequency domain analysis of these guys in electronics too. I see you guys making faces. It's one of my favorite things to teach. You guys are going to hate. It's so interesting, but it's very, very mathematically rigorous. So for now, effectively, you're going to have to take it on faith that between the gate and the source terminals, even in our small signal model, we should see a capacitor, which is effectively just going to look like an open circuit. So there's really nothing for us to worry about there. Okay. So with that taken care of, the next thing that we talked about for our BJTs was what happened when the early effects were present. So we can do something similar with a MOSFET, but what happens when channel length modulation is present? So when channel length modulation is present, once again, we have an increase in our drain current as a function of our voltage, in this case, VDS, right? And it's a linear relationship between our drain current and VDS. So we'll have a resistor R naught that is just the partial derivative of VDS with respect to ID. And this winds up becoming simply 1 over lambda ID. So putting all of these results together, we get the following small signal model for a MOSFET. So here's our gate. Here's our small signal voltage, excuse me, VGS. This one doesn't get some new name for arbitrary reasons. So VGS is still just going to be VGS. There's no V pi equivalent type thing. Then we have GM VGS here. So this is our effectively small signal drain current due to a change in VGS. Here's our resistance R naught that's taking into account the effects of channel length modulation. Here's our body effect transconductance multiplied by our small signal source to body voltage. Here's our drain. This is our source terminal. Down here will be our body terminal. And so this is our small signal source to body voltage. We will pretty much only see the body effect in integrated circuits. So when we're dealing with a discrete 3-terminal device, we're always going to assume that the source and the body are tied together, which means a short circuit here results in an open circuit here. So the body terminal literally does nothing whatsoever, and we'll just have VGS, GM VGS, and R naught like so. So anytime that our source and our body are tied together, or anytime that we're dealing with a discrete device where effectively internally, the source and the body are fused together. We're going to throw away our body effect transconductance parameter, and we're going to short the source body hole. And let's see. That's our small signal drain current ID, which is the only current in a MOSFET. All right. So we have all of the different pieces and parts here. One thing that I want to potentially clarify in case it was not obvious, all of our small signal parameters, our transconductances, our resistances, and all of that kind of stuff are set by the values of our DC operating point, right? So we have to know what's going on at DC in order to have any clue of what's going on at small signal or AC. So in order to calculate any of these quantities, it is literally the exact stuff that I've been having you guys do for the past couple of weeks. Those relationships and all of that kind of stuff still matter. But for the most part now, we're going to effectively assume that since we have all of that sorted out, none of it actually matters. And we're just going to be off to the races with this kind of stuff. So what I want to talk about now, and this will be our last topic for today, is actually a recap of something that we talked about way back in Circuits 2 on our first or second day of class, where we were talking about amplifier circuits in general. So we, way back in Circuits 2, came up with a model for an op amp. That looked something like this. So we had some input resistance. These were the terminals across which we applied our input voltage. And then we had our voltage gain multiplied by our input voltage. Here's a resistance R out. And here is our output voltage, V out. And we said that our amplifier was effectively fully described by three quantities. Our input resistance, R in, our output resistance, R out, and our voltage gain. If we knew those three quantities for our amplifier, it doesn't matter how internally complicated the amplifier was, we could use this circuit and effectively come up with the same result. We are going to take this approach to transistor amplifiers. And I just want to show you guys something. This really doesn't have a whole heck of a lot with what we're about to talk about, but I showed this to Jake the other day and I thought it was pretty interesting. Let me do this in blue underneath. What if I source transform this practical voltage source here into a practical current source? So this is going to be a transconductance gain, so I'll call this AG. What does this look like? Well, if I call this guy right here, I don't know, maybe my base, and this guy my collector, and this node down here my emitter, it's effectively exactly the small signal model of our BJT from the jump. In a MOSFET, we have already explained that our input resistance is effectively infinite, so we would just replace that with an open circuit. Okay. So anyway, so this small signal model is already directly in front of us, or this practical amplifier model is effectively already directly in front of us. All right, so the last thing that I want to talk about for today is measuring RN, or I say measuring, determining RN, determining R out, and determining the voltage gain, right? So yep. R out. So determining our voltage gain is going to be pretty darn straightforward, right? Effectively, our voltage gain, and we're going to treat all of these transistor amplifiers that we're going to be dealing with as small signal voltage amplifiers. It is literally just going to be the ratio of our small signal output voltage to our small signal input voltage. So we are just going to have to do some circuit analysis to figure out what V out as a function of V in is, and then divide both sides by V in to give us our voltage. That's all we're going to do. We're going to do it a whole hell of a lot. Okay. That's one of the easiest things to do. Okay. Now let's talk about how we determine our input resistance. Okay. So to determine our input resistance, let's say that we have an arbitrary black box network representative of any of the circuits that we're going to be dealing with. Here's the input terminals of our network. Here are the output terminals of our network. So we are going to apply a test source to the input, measure the current flowing into the network with our output terminals open circuited. And our input resistance will simply be the ratio of V test divided by I test. So this is our process 100% of the time for determining the input resistance of our network. I would say 90% of the time, I'm not even going to bother applying a test voltage. I'm literally just going to use V in there, because once we figure out what the current is that's leaving our input voltage source, we have all of it. And then lastly, let's determine R. Okay. So same situation. I've got my black box network. I'm just writing in and out over here. So when we determine R out, we're going to apply our test source, almost always a voltage, across the output terminals, measure the current flowing in with our input terminals short circuited. And let's say that R out in this case will still simply be the ratio of V test divided by I. And so let's just put this into practice for a very simple circuit. So let's say that I have the following circuit. That just, let me move this over. VBE, so some DC base emitter voltage necessary to bias this device in the forward active region, and then superimposed on top of that, we'll talk about how that actually happens. It's just some small signal input voltage, right? So this is what our circuit looks like. Our small signal analysis, so that we can figure out what our small signal voltage gain, our small signal input resistance, and our small signal output resistance is going to be, we need to turn off our DC sources, much like we did earlier. And then we're going to use our small signal model. Let's make this even easier. And let's say that early effects are not present. Okay. So our small signal model should look something like this. So here is our base. Here's our resistance R pi, over which we have some voltage V pi. Here's our current GM V pi. Since the early effect is not included, that means the resistor over here should be an open circuit. So here is our collector terminal. Our emitter is at ground by inspection. So there's our small signal model. Now let's connect the rest of the network. So we have our input voltage being applied between the base terminal and ground. Our resistor RC is connected between the collector and an AC ground is what I'll refer it to. So that positive supply voltage VCC is going to look like ground in our small signal model. And our output voltage is measured between the collector terminal and ground. So this is what the small signal model representation of this large signal circuit will be. So let's figure out our voltage gain first. So anybody have any thoughts on what our voltage gain would be? Or how, let's start with our output voltage. Anybody have any thoughts on what our output voltage? So our output voltage is just the voltage drop across this resistor RC. What's the current flowing through the resistor RC? Negative GMV pi. Absolutely. So negative GMV pi is flowing in, or excuse me, GMV pi is flowing into the negative polarity terminal and then down around to the emitter. Okay. So V out is equal to negative GM V pi RC. All right. How is V pi related to Vn? They're the same thing. The positive polarity terminal of Vn is at the base terminal, the negative polarity terminal is at ground. The positive polarity terminal of V pi is the base, the negative polarity terminal is at ground. So that means this is negative GM RC times Vn. From this, our small signal voltage gain is negative GM RC. One down. Now let's figure out Rn. So figure out Rn. Let's just use Vn as it is as our test source. And so this is the current IN that we need to find. And then the ratio of Vn to that current IN will be our input resistance. IN is the current flowing through resistor R pi. So IN is just V pi over R pi. So what's Rn? Let's write some things down here. I think you lost a little something here, right? So we found IN by inspection to be V pi over R pi. From this, capital Rn will be V pi divided by V pi divided by R pi, which is just R pi. Now, to find R out, we turn off our input voltage source, which is the same as us shorting out those input terminals. What's V pi now? So how much current is flowing through this guy? So what resistance do we see looking in? RC. That's it. We just analyzed our first transistor amplifier circuit. The easiest possible one to do, to be very, very clear, but we just analyzed our first one. So now let's throw you guys a curveball because we've got 2 minutes left. Let's say that this was a MOSFET. What would the only difference in our small signal model be? This would be an open circuit now. Everything else would be exactly the same. So we are only going to bother with analyzing BJT amplifiers
Because effectively, if we take the limit of our BJT amplifier as we let Rn approach infinity, it's the exact same thing as doing a MOSFET. So we're gonna spend 95% of our time looking at BJTs and then be like, what does this look like in R when Rn is infinity or R pi is infinity, and then just use that for our MOSFET relationship. There's no reason to analyze the circuit again. It's the same damn thing. All right, I'm done.